Well, thank you very much, Rita and Carlos and everyone else for your very kind invitation here to Agasu. I'm very glad to be my first visit, and I'm very glad to be here. I told my family I was coming here, and they were extremely impressed. But it turned out that they'd looked it up on the web, and they thought it was the asteroid. So there's an asteroid, apparently, Agasu. Excuse me. I was asked to give a very general introduction about black holes as cosmic matters, as we call them, or dynamos. And I've tried to do this in two ways. One, I'm very conscious, and I'd like, and so as I know there are a lot of students here in the audience, or at least I've just discovered that. I'm going to give a very sort of general introduction to some of the topics that I will cover, but others will also cover in this conference. So there's a lot of material here, and I'm very conscious of that. Firstly, don't worry, because almost everything I say by way of introduction will be repeated in a subsequent talk. And the second point is, this will be an excellent opportunity to interrupt, to ask questions. And so I'm going to encourage particularly the students, or anyone who's unfamiliar with this material, to stop and ask questions. Okay, so I think this is going to be a much more successful meeting if we establish this tradition in it. So please do that, and don't worry about exhibiting what you don't know. We may not know either. So do go ahead and ask those questions. The second thing is I've got much more material that I'm likely to be able to cover in an hour. So I'm happy to go on for 3 hours, or alternatively, I may just not cover it. That's fine too. We can discuss it in some other forum later. But so we'll just see how we go. I have to say, I just made a discovery about black holes about a month ago. Is that you can make money off them. This you can actually come out very well. I was on vacation in California, and there's now a black hole winery there. It has a picture. It's called the Event Horizon machine, and it's got pictures of black holes and rather dubious orbits around it. So there's great commercial possibilities in this field. Do not forget that. I'm sure any wine in Brazil was better than the contents of this bottle, which was pretty dreadful. But that was my big discovery on black holes lately. Okay, all right. So let me start off a little historically. Probably a precedence for this, that the person who's usually credited with having thought about it was a sort of an amateur scientist at some level, though he had been a professor of geology before that, called John Michel. And he had, in those days, if you got married, you had to leave academic life. So he did, and he became a priest in Yorkshire, and he invented lots of things, including permanent magnets, seismology. He realized that earthquakes were seismic waves, and understood an awful lot about geology and mechanics. But one of his ideas, almost a throwaway idea, was what would happen if a body like the sun became so collapsed that the light was unable to escape its surface. And he started thinking a little bit about this, and that, of course, we now think of as a black hole. And Laplace also had the same sort of idea. It wasn't until the advent of general relativity that Carl Schwarzschild, he didn't know this, but he actually had written down the solution of the equations of general relativity, which a year earlier had been realized by Albert Einstein. And those equations, although he didn't fully appreciate their significance because he died very shortly afterwards, this all happened during the First World War, describe a spherically symmetric black hole, okay, which has lots of properties. I'm not going to go through these. I suspect most people here who's never heard of a black hole? Let's try that one. Okay, all right. So who feels that they have some understanding of the basics of black holes, perhaps from some course in GR? Is that reasonable? Who's never seen any general relativity? Okay, that's great. So we've got some good starting point. Okay, so one of the things that comes out of this, and this is from a Newtonian description as well as a relativistic description, is that if the escape velocity is the speed of light, then you can associate a radius with it, with the mass in direct proportion like this. And that will be the radius, a radius of the event horizon. You might say, well, space-time is curved. What does that mean? What it really means is, let's take the circumference, and it's that divided by 2 pi. Let's measure it with meter sticks. It's a rather difficult experiment. We can imagine doing it and taking a limit. And let's take an area, for example, and divide that by 4 pi and take the square root. And there'll be, in this context, a definition of the radius. You don't have to go into the black hole with your meter sticks to do this. Okay, so let's go forward to the 1960s, the early 1960s, when there was a revolution in some sense of solving the equations of general relativity, and many things were discovered. Here's John Wheeler, who in the United States, there are plenty of others, really took this whole idea very seriously. In fact, he didn't actually coin the phrase black hole, although he was accredited with it. It was an Australian journalist called Anne Ewing who did that, but he took, I don't know whether he knew about it or it was a coincidence, but she was the first person to use this expression, black hole. Here's Roy Kerr, who in a sort of miraculous piece of mathematics discovered a solution to the same equations that Schwarzschild had been dealing with, and this described the spinning black hole. So it is non-spherical. I'm going to go through those equations, but you can do that in the course in relativity. I will bring out some features of the solution. At that time, it was just a solution, but as far as astrophysics is concerned, it is the solution. And as far as what one observes at the moment, using telescopes, this is all we need. It's just this solution. There are extensions of it, including charge and so on, and lots of other ones in different dimensions and all of that, that incorporate the full febrile imaginations of theoretical physicists. But as far as astrophysics is concerned, it's only this Kerr solution is the only one we'll need. Okay. Some of the properties were understood, particularly by Roger Penrose, and who I just actually spent some time with, and Stephen Hawking, who's here, I think, somewhere. There we go. Who recently passed away, and somebody we all knew in the 1970s when he was doing all of this, well, in the 1960s and 70s when he was doing this work on black holes. And so let me summarize what they and many other people did. And basically they showed that it's like, it really is like an elementary particle. You can just describe it by mass and spin. You can't actually describe it by charge as well, but the charge is going to be effectively zero under astrophysical circumstances for the holes we know about. So here is just a summary of what comes out of all of this complicated mathematical physics. All right, and this is what I'll need for this talk. These are the sort of take-home messages. Getting there is a serious amount of work. But first thing is, and this is, I'm going to go through a lot of physics here in a very shallow way, but you'll get some idea of the context when we're talking about the black holes themselves, which is half your title. Okay, the first thing is, if we talk about the spinning black hole, and this is now generalized not just to the Schwarzschild holes, but the spinning Kerr black holes. You take the area, we can define in a formal mathematical way the area of this surface from which you cannot escape, the so-called event horizon. This is it's not a physical surface, it's a surface that we can define geometrically. And we can define quite formally, despite being a curved space-time, an area associated with it. And this area has remarkable properties. One of them is, it was originally an analogy, which is the way that Bekenstein, who first realized this, thought about it. It was a bit like entropy. And there's a theorem that under sort of classical processes, standard classical processes, that area always has to increase. So in that sense, it's like entropy. But it was just an analogy. It was a good one, it was productive. But Hawking showed that, in fact, it was not an analogy, it was an identity. because we could make that area into an entropy, which meant the black holes had a temperature. And that's Hawking radiation. Now that was a tremendously important step forward in understanding the quantum mechanical properties of black holes. There's no evidence that this has got anything to do with astronomy as yet. People, including myself, have looked for sort of tiny black holes that would exhibit the effects of having a finite temperature, and there's no evidence that they exist, and in fact they would be terribly hard to make. But it's, you know, it's still worth looking, but there's no evidence that they're there. So just take it from me that this area has to increase. So if it's got to increase, I can define an effective radius. This is just a formal mathematical definition. I'm just going to define an effective radius by just pretending it's like a sphere in Euclidean space. But I can also define a mass associated with it. And this mass I'm going to call an irreducible mass, or M0. I'm using a suggested notation here. I'll just call it M sub 0, an irreducible mass. And I call it irreducible because the entropy can't decrease by classical processes, the sort that we're talking about. And that means this irreducible mass, M0, cannot decrease. So this irreducible mass it's always got to increase in classical processes. All right? That's what we see in astrophysics. Now, if we say this hole is spinning, then that means we can associate an angular momentum with this mass. And here I've got encapsulated, so quite important that is, you might say, well, angular momentum, that involves mass and all of that. This is a specific angular momentum. It's the angular momentum per unit mass of the black hole. Now, I said mass, not irreducible mass. This mass is different from the M0 here. The mass itself is what Johannes Kepler or whatever would measure for a satellite in a distant orbit around this object, this black hole. If they measure the radius of that orbit at a very large distance and measure the period, then you can get the mass in the same sort of way that somebody working in the solar system would do. Okay? So that's the mass. And that is the actual definition of the mass. Now, as we did on the first slide, we can convert that into an equivalent distance just by multiplying by g and dividing by c squared. That has the dimensions of distance then. So I'll just use this mass as measured now in distance. All right? So it's like setting g and c equal to 1 in a unit system. And that's just fine. I don't need Planck's constant. I can just do that. So that's the mass. So if we ask, what is the specific angular momentum? This is the angular momentum of the black hole, and that can also be measured by a gyroscope. A gyroscope will precess in this field, and that defines essentially operationally the angular momentum. So that angular momentum will have, as defined, a value r0 squared omega. Now you might say angular momentum per unit mass should be velocity times distance, but the velocity, the speed of light has been set equal to 1. So we can consider angular momentum as being the effective distance. We set it equal to 1. And one of the theorems that comes out of this mathematical physics is that the specific angular momentum must be less than the mass. Now, the mass is m, the reduced mass is m0. So the specific angular momentum must be less than mass. Otherwise, you get solutions that are not physical, basically. We can then just formulate. The idea is, because it brings up an analogy, it's not terribly useful, but it's interesting. We can define a rotational speed. And I'm going to define it as the angular velocity. This is the angular velocity. Sorry, I should have said there's an angular velocity as well as an angular momentum we can define for the black hole. The angular velocity is if you imagine going as close as you can to the event horizon, then it turns out you have to rotate with the black hole. And that angular velocity as measured by a distant, that rate of rotation as measured by a distant observer is essentially the operational definition of the angular velocity. Now, I think somebody at the back was they may have been scratching their head or trying to break the ice by asking a question. This is wonderful if that was true. Is somebody asking a question at the back? No, he's scratching his head. Okay, sorry. Okay, so if anybody doesn't want to scratch their head but ask a question, please do. Okay. All right, maybe it'll happen, maybe not. Okay, all right, now there's another little theorem that comes out of this business, and I've called this here, obviously I'm thinking about a first course in special relativity here as an analogy, no more than that. I can define the rotational speed, which is this angular velocity times this effective radius of gyration, if you like. We can call it that if you want. And I'm going to, it's in the speed of, in units of the speed of light, so I'll call it beta. All right, this just sounds like one dimension, you know, special relativity in one dimension. All right, and it turns out one of these theorems says this beta, unlike in one dimension, is limited by 1 over root 2. Okay, that's the maximum value it can have. And then we find that the relation between the mass and the irreducible mass is given by this formula here, which you may have seen in some old textbook on special relativity. Now, this has got nothing to do with special relativity, it's got nothing to do with this, but you will remember it now, because you remember this old formula about saying, people don't think about this nowadays quite in this language, but they think about a mass related to a rest mass, if it's moving with a speed v to c. So that tells you that the mass m0 must be greater than 0.71 m. And there's a terribly important message that comes out of this that's central to everything I'm going to be saying. A terribly important message. There's a finite amount of mass that you can, that is in excess of the irreducible mass. And if we make the black hole spin as fast as it can to have a specific angular momentum equal to its mass, then essentially you've got 29% of the mass energy of the black hole. It's associated with rotation, and in principle it can be extracted. So just like doing elementary thermodynamics, that's where some of this thermodynamics comes in. Just like doing elementary thermodynamics, you've got some accessible energy, but you can't take infinite amounts of energy out of a thermodynamic system because of the second law of thermodynamics. It's essentially a second law here. We can just take up to 29% of the rest mass energy times c squared out of that spinning body and use it to gratify astronomers and make things shine in the dark and all of that. Okay, so up to 29%. Now, in real life, of course, you're not perfectly efficient in the same way that an automobile refrigerator is not up to the Carnot limit given by thermodynamics. So you're going to be more like 10 or 15%. But still, that's an awful lot of batteries, to use your expression, the batteries that power that clock you kindly gave us. So that's an awful lot of those. We'll come to that point in a bit. So this is the sort of key understanding that led to the possibilities that I and many other speakers are going to describe here. Does anybody want to ask questions about this? Because there's energy that's up there for the taking associated with the spin. It's a finite amount, but it's a lot.
Professor, would you mind explaining
Basically, it comes from considering the solution of the equations of general relativity for a Kerr metric. And then we ask, what's the maximum amount we can what the maximum rotation speed we can have for that black hole, and still have an event horizon surrounding it. And basically what you find is, if you start with a slowly rotating black hole and you throw things at it in the right side, you can speed it up. But as you keep on trying to speed it up, however much you throw it, there's a limit to how far you can go. You can find solutions that have faster spinning holes, but they have what are called, they have exposed or naked singularities. Okay, and those are unattainable, just like our tachyon solutions to special relativity. They're like, you can go faster than the speed of light, sort of in algebra, but in practice you can't get there. Okay, so very good question. Thank you very much. You broke the ice. You may now stretch your head. Okay, thank you. Okay, so that's sort of kind of central. Okay, now I'm now going to go, having got that point there, I'm going to spend quite a bit of time doing astronomy. So how many here would regard themselves as astronomers? Who here would regard themselves? Okay, so a few. How many would not regard themselves as astronomers and think of themselves as physicists? So that's most of you may be in the wrong meeting. We're talking. So what would the rest of you who have not put up a hand regard yourself as? If you're not an astronomer and you're not a physicist, what would you regard yourself as? Anybody want to admit to some other profession? So I take it you're all too shy to announce yourselves as astronomers or physicists. So I'll assume that some are astronomers and some aren't. Okay, so this is the astronomy bit. This is the relevant astronomy, an awful lot of jargon and phenomenology and things that have come out of the business end of telescopes and so on. Okay, and I'm just going to say, subsequent talks will say a lot more about these, I'm confident. Okay, so this is a little bit historical. And obviously I'm sort of zooming in onto the black holes in astronomy. So this is the first, it's just over a century ago at the Lick Observatory, looked at what we now, the Seaford Galaxy, what we now call a Seaford Galaxy, NGC 1068. So that's an awful lot of astronomy, which means there's an awful lot of words there without definition. And the definitions are never too good anyway. That NGC means it belongs to a catalogue. That's not a great definition, but that's what it is. And this is the so-called Seaford Galaxy, and it was shown to have an active nucleus. And this was the first sign that the nuclei of galaxies were gravitational potential wells, because gas was moving at high speed. So we can see there was something going on at the center that's defined by gravitational potential well. And that was a remarkable discovery. An equal remarkable discovery at the same telescope was made in 1918, so this is a century ago. This was what we now call Virgo A or M87, various other names it has. This is a modern picture, not one that's taken out of photographic plates then. And basically it was that, well, it wasn't, people went, Curtis actually knew, but the others didn't, that this is a galaxy like our own far away. And in this was what he called a curious straight ray. And that curious straight ray was sort of a feature there, and that is what we now in modern language call a jet. And that will be central to a lot of what I'll talk about. It's the first sort of observation in optical astronomy of a jet. And so there's a whole lot of taxonomy and jargon here. Sometimes they say if you get the illusion that this is astronomers belong to the world's second oldest profession. So they spent a long time naming things and defining classifications and so on. They never die. This is one that shouldn't have died because it's actually useful. It's FR stands for two people, friends of mine, Fanneroff and Riley. So this is a Fanneroff and Riley class 1 division of radio sources. So I'll use FR1, and I'm sure other speakers will unconsciously fall into this jargon too. And these are low power radio sources. These are sources as observed as radio sources. Nowadays, what's sort of key about this is we have very strong evidence that there's a black hole sitting at the center of that galaxy. That galaxy, like all galaxies worth the name, reasonable galaxies, has a black hole in its center. We have evidence of that. I'll show you some of the evidence. And associated with that is a jet, a linear feature. And that is material that is escaping from that black hole in one direction, and that is moving with speeds very close to that of light. Of course, Curtis didn't know that, but we know that now. And a point I'll make, and I'll make it several times, that in sources like this, as far as we can measure it, the power in those jets is very much greater than the rest of the power associated with the nucleus. So this is not some sort of afterthought, this is it. Okay? So that's people are only recently coming to terms with that, but that's what it is. Here's another famous observation. I'm not sure why I was prompted to recognize this, but it's a big discovery. It was actually discovered by Grote-Reber, who was an amateur, radio amateur and working in the 1940s. It's a big source in the sky. It was a radio star in those days. It was just a radio source detected by radio telescopes. Remember, there's 70 octaves of electromagnetic spectra out there for astronomers to use. It's not just our eyes. These guys were just using visual. Okay, but that's just one octave. There's 70 octaves for electromagnetic spectrum. We use pretty well all of them now. There's also, as I'll emphasize, another 70 octaves of non-electromagnetic spectra. And they're part of the story too. We'll get to that. Anyway, this had been discovered in the 1940s. Then in 1953, in one of the first attempts to do interferometry with radio telescopes, two radio astronomers, Jensen and Dasgupta, showed that it wasn't a sort of point source essentially, it wasn't or a sphere or something that you might have expected. It was two sources. And that was the first recognition of a double radio source. These are called double radio sources, two sources. And it was very soon identified in 1954 by Barter and Minkowski with a galaxy rather similar in spirit to this, but much further away. Very much, lot further away. And the galaxy sat in the middle of it. So we have these two regions of radio emission on either side of a galaxy. Sorry, I thought I had a picture. I'll show you pictures of what it looks like today. And just to cut to the chase, the center of this galaxy contains a black hole, and jets fuel these two, what we call lobes, we call them lobes of radio emission, two sources on either side. So there's two jets, one going that way, one going the opposite direction. And they're conduits of energy, momentum, magnetic flux, anything else you want to get rid of. It's going out there into these two lobes of radio emission. Okay? And the power, what was realized then, and in fact we now know it's a somewhat stronger statement, was that the power in this radio source, the simple power, was greater than that of a galaxy. So something happening in the black hole, no bigger in size than the solar system, is producing as much power as the rest of the galaxy. That realization only got worse in 1963 when Martin Schmidt, working with radio positions produced by Cyril Hazard, discovered the first quasar. And this was a very high redshift, 3 times the distance of Cygnus A, and the power associated with this, he was seen as an optical phenomenon first of all. He was seen as a radio phenomenon, seen as a radio phenomenon and an optical phenomenon, Seen first as a radio phenomenon, then as an optical phenomenon. But most of the power in this source turned out to be in the optical, and it was all then seen to be 100 times the typical power of a galaxy. Power or luminosity. Now, astronomers usually say luminosity rather than power. It's the same thing. Okay? Watts. So this was enormous, and this was at high redshift. These are the quasars. Okay, so quasars are operationally active, more jargon here, active galactic nuclei. These are galaxies that are shining, nuclei galaxies that are shining, we call them active galactic nuclei. The active galactic nuclei have power that's much greater. If it exceeds that of a massive galaxy, then we call it a quasar. There's actually a better completely arbitrary definition than that, but that's basically what we need to know. If it's brighter than a galaxy, it's a quasar. If it's less, it's some other type of active galactic nucleus and not quite as active. Okay, let's move on. Now we can measure the masses of these things. Not entirely sure what I've done here, but okay. The black holes themselves, this is sort of, I went to the first indications, but in the 1960s, X-ray astronomy began. And although people didn't understand what they were looking at the time, they were starting to observe black holes as well as neutron stars and so on in binary systems. So there's a regular star and then a companion star, which isn't another regular star, it's either a black hole or a neutron star or a white dwarf sometimes. And when those three possibilities happen, then you can get gas transferred from the regular star to the black hole or the neutron star. It's got a lot of angular momentum, so it usually makes a disk of some sort. And like Saturn's rings, they're called an accretion disk, of course, accretion disk. And that is a binary X-ray source. And some of these were shown to be associated with black holes. This first happened in 1971 when observations of a source called Cygnus X1. You could argue on the basis of these astronomical observations that the mass of the compact object that was the companion to a regular star was, in modern measurements, it's about 15 solar masses. It's changed a little over the years, but the key thing that hasn't changed is that it's comfortably larger than the maximum possible mass of a neutron star. So the way the argument at some level still does, but there's a bit more to it than that now, is that it's a compact object, it cannot be a neutron star, therefore it's a black hole. Okay, now we have more circumstantial evidence that it really is a black hole than that. But we know of no physics alternative that's heavier than a neutron star other than collapse to make a black hole. Essentially, a neutron star that's more than, so we say, 2.8 solar masses, and that maximum mass is probably a little less than that, if you can put a comfortable band of 2.8 solar masses, cannot support itself against gravity and must collapse. Okay, so that's something you can just demonstrate using conventional physics. Okay, so that's this one here. Going back to the galactic nuclei, then I said all galaxies worth the name, and that includes our own, which, although it doesn't know it, it doesn't answer to this, but it's called Sagittarius. Sometimes it's called the Milky Way, and there's a constellation called Sagittarius, and that's where its center is. And the sources there of infrared and radio emission and so on called Sagittarius A star, and that we now know very confidently is a compact mass, and there's no credible theoretical alternative to it being a black hole. People have tried all sorts of sort of counterintuitive ideas, but even those won't hold up to rigorous examination. And so there's every reason to believe that we've got a black hole of 4 million solar masses. It's an exceedingly inactive galactic nucleus. It's not an active galactic, it's semi-inactive. Do not be ashamed. You would not want to share a galaxy with a quasar. It would not be nice. And you would, we would be mutating at a rather splendid rate as a species if that were the case. So we may have been active in the past. Our galaxy there's also evidence that it was more active. How active is a matter of debate. It was, we almost certainly never a quasar. It was what's called a seedless galaxy. That could have happened. But at the moment, we have an exceedingly inert, inactive, sleeping giant at the center of our galaxy with a mass of 4 million solar masses. How do we know that? We know that, I think it's going to work here, because we can observe stars in orbit about, is that going? Yes. You can observe, I think there, if you can see it, stars in orbit. These are actual orbits that are measured of stars going around us like planets going around the sun. And on that basis, you can measure the mass, and it's 4 million solar masses. In April, there was just a pass of one of these stars, relatively close by to the center on a highly elliptical orbit, and that happened for the second time quite recently. So this is very confident Newtonian mechanics. You know what the mass is. Let's go back. Oh, sorry. Let's go back to M87. There we can use stars and gas to give similar but not identical answers. And there, I think the best informed guess is the mass is not a few million solar masses, it's a few billion, 6 billion solar masses. Okay? And the most massive, and we can see gas in orbit, and so we know which way around it's going. And we can see stars in orbit too, so that's 6 billion solar masses. And the most massive one, you mentioned the Guinness Book. So this is another entry in the Guinness Book, I believe. It's the most credible, the largest credible measurement of masses. You can find things out there in the literature that are incredible, but this is credible, is 20 billion solar masses. Okay, make that absolutely sure. So from a few million to 20 billion is the range of the massive black holes in the galactic nuclei. Everyone happy with this? To whom is this a new statement? To whom is this completely new material? Don't be afraid to say. Okay, I should obviously speed up then. You only have yourself to blame by not admitting that this is all quite familiar. Okay, all right. So the other thing, I said there were two things that characterize the black hole, and the other was the spin. This can be measured too. And I'm going to come back to this a little bit, but basically the most reliable technique is to look at the shapes of iron lines in the X-ray, using X-ray telescopes from gas in orbit in the accretion disk. And it turns out the accretion disk, about which I have relatively little to say, there's a limit to how close they can get to the black hole, and the faster the black hole spins, the closer in you can get, and therefore the broader the lines become. There's more, again, there's more to these arguments than I'm betraying here. But you find that many of these objects have spins that are quite close to the maximum they're allowed to have by general relativity. So they have a up close to m, or omega, the angular frequency, has near to its maximum value. And so we have these fluorescent iron lines, and I'll say a bit more about this later on. And then we can use other arguments and so on. And I say, if there's time, I'll return to this point. Okay. So let me just say a little bit more about the jets. I'm going to start talking more about the jets. Again, this is observational astronomy. We're going to do quite a lot of it, and then I'm going to put it on one side. So this is M87. I'm just using it as an example. It's one of the best examples. It's in a cluster, Virgo cluster, which is a giant X-ray source. That X-ray source appears to be heated by the activity of the black hole in the galaxies, in that black holes in the galaxies in that cluster, and especially the one in M87. There are jets that we now observe in radio, X-ray, gamma rays, as well as in the optical, and this is what it looks like at X-rays. And it has a lot of power associated with it, much more power than we associate with the center of with the nucleus of the galaxy. Probably 100 times, at least 100 times that. So the jet is carrying more power than the accretion disk is radiating in sources like this. That's a very important point. Using very long X-line interferometry, which essentially puts telescopes on radio telescopes on different continents and has a corresponding large baseline, you can do micro-arc second resolution. Again, I'll return to this later. And you can see structure arguably with model fitting and so on down to 10M, I think more comfortably down to about 30M. M, remember, is the size of the black hole. It's a characteristic linear size. And so we're starting to look at these features, the region around them. So the people who are optimistic will say we're model fitting down to about 10M, others would say really you're only really imaging to about 30M, but it's somewhere in there there's a distinction. And what you see if you look at the jet on not quite the smallest scale yet, you resolve a bit and I'll show an image later on. But what I want you to notice here is when you look up this jet up front and personal, if you look at it very close in, you can see the shape of the profile, which looks like, on this resolution, look paraboloidal, but the emission is coming not from the center of the jet, from essentially the walls of the jet, from the surface of the jet. Okay? And if you think about this as a flow, you should think about it as a boundary layer. Again, I'll return to this point later on. So this is observational evidence, and what you're seeing is emission from the walls of the jet. Here's 36273, which I mentioned. There's the galaxy, here's the jet. In this case, it's much larger. The quasar's about 10 times the galaxy luminosity. The jet itself exhibits a phenomenon that was predicted, called superluminal expansion, which means it has features that appear to move faster than the speed of light. What that means is the sun that's coming towards you, like that, it's moving just less than the speed of light. Because of light travel time effects, the transverse distance across the sky appears to exceed the speed of light. And here's one of the first pieces of observation that showed this. You're going from 1977 to 1980. You expanded by 30 light years in 3 years, so it's going at 10 times the speed of light. That was shown in early VLBI. We now know you can get it from these sources about 30 times the speed of light. And it's just pure kinematics that does this. But one of the important consequences of this is that if you've got material that's moving almost at the speed of light, by relativistic aberration or the searchlight effect, it will beam its emission along its direction of motion. So that means if I just got a random active galactic nucleus with a random jet, and say it's going off in that direction like that, and it'll have a counterjet in that direction like that, then you will see it not particularly bright. But if I orient it like this, so someone at the back here, say at the camera, like that, look at the camera, it's pointed essentially in your direction, it will look extraordinarily bright because it's beaming its radiation in your direction. It's relativistic aberration, if you like, or the searchlight effect. It'll look very bright. And so when an astronomer looks at a flux-limited sample of these sources, it's going to see preferentially those that are pointed in your direction. It's not an excuse for paranoia. It is, these are just going to appear brighter, and therefore that's what the astronomers will look at, preferentially. When that happens, there's a word here, etymology I need not rehearse, called blazars. And most of these objects are now called blazars. And in fact, there are two, as always, there are two types of blazar. There are the low-power version, which are called BL-LAC objects, and the high-power version, which are quasars or sometimes flat-spectrum radio quasars. So that's just taxonomy, it's just names, but it actually means something physically. Again, we may have time to interpret it. It certainly means something observationally. So here's 36273, and of course, as discovered early on, this is a polarization of the jet, which shows the strong magnetic fields there, and it's highly variable. This was discovered early on. Again, I'll return to this. Here's the spectrum here. So again, I'll return to this. So it's got variability in this case in timescales. In the Gammarays, it varies on timescales for about 10 hours, and that's again very short. This is, we're talking about something that a black hole, a billion solar masses, it's as big as the solar system. All right, it's making this jet and outshining the whole of the decent. Here's another one. This is a low power blazar, as I just said. It's called. These are called in the trade a BL-LAC object after the variable star, which it wasn't. BL-30. This is another one known as Carryin 501, featured in the movie Contact. You're old enough to remember that. And actually, it was called Carryin 401 because my graduate student was an advisor to the movie and got it wrong. No, it wasn't called. It was called Carryin 521. That's what it was called. I think if you go back to the movie, but never mind. It's right. It's about a 300 million solar mass black hole. It's spinning. There's a jet there. There's gamma rays there. And here we see variation in those gamma rays on timescales of 2 minutes. Very compact, very rapid, very active. Very powerful as well. So I said I'd show you some more. These are more jets. Rather beautiful. I did mention the first of these double radio sources, Cygnus A. This is what it looks like now. There's a galaxy there, an elliptical galaxy like that. There's the nucleus, that bright spot there. Here are the two jets. You can sort of trace them. The one to the left is a bit more of the eye of faith, but it is there. you see the one to the right, and this is a conduit that's fueling this lobe of radio emission here, and it terminates in so-called hotspots. That's one hotspot there, there's another one up there. And it terminates in these hotspots where it comes to an end. And you see it very bright in radio, you see X-rays, you see giant emission like that around here. But most of the power that you know about comes out eventually from these giant radio lobes. Here's another one, with some affection from the 1970s. And right at the center there is a black hole. There's a dead straight jet coming out of it. Here's picture A. You can see this is the most spectacular one of all. This is an X-ray observation. There's a black hole here. What I can only describe with the particle physics, this is a beam dump up here. This is the hot spot. This is a dead straight X-ray jet that goes out way outside the galaxy and fuels double radio source around here. Seen in X-rays. These are radio observations. You can stick them in binary systems. You can cause them to process. You can have them double, two jets in the same galaxy. There's 10,000 of these things, okay? We've mapped and imaged and so on. Here's the galactic one, SS433. Felix is going to tell you, I'm not sure how much he's going to say about SS433, but he's going to tell you about the galactic superluminals for sure. And I'll say less about that because he's going to give you everything about those. But here's SS433. This is, we now pretty confident believe, is a black hole in a binary system. Actually, my own view is that what causes all of this is in a triple system. I think it's actually a triple system that's causing dynamics. But the key thing here is this jet that we can see. In this case, it expands at a quarter of the speed of light, processes with a 161-day period. Okay, so that's the galactic black hole. I said the VLBI observations, these are modern ones. Remember, I drew attention to the fact that the jets, here's the M87 jet, seen here. There's actually other observations of this, but this is the one we've got right now. It's edge brightened, and it looks like we've got an outflow here from a black hole that's in the center here. They're collimated within 100 times the size of the black hole, and the emission comes, as I say, from these walls, if you like, of the jet, and I'm going to use the suggested term. I'm going to describe those as boundary layers. So if you've got a jet of outflowing material, it's interacting with its surroundings, and there's a boundary layer. You would say in fluid mechanics, just like airflow over an airfoil in an airplane, for example. There's a boundary layer there. Okay, and that's what we're seeing. Here's another example. These are very exciting observations. They're on a much larger scale, but they're even more suggestive than the M87. This is in another nearby galaxy, sometimes called 3C84 or Perseus A. Again, we can see rather graphically this boundary layer emission on either side. Okay, that's where most of the emission is coming from. And this is synchrotron radiation, by the way, relativistic electrons. We're almost sure about that. There's a black hole right in the middle there. And the point is, this is an example of a jet that appears to essentially expand. Okay, I know this is going to work. Think not unreasonably of this organ here as being a black hole, and two jets coming out like that. Okay, so what the jets seem to do is the flow seems to go out almost equatorially and then almost bend, become two jets coming like that. That's what it looks like morphologically. You just look at the image. Again, I think this is a very recent observation. This is only done about 3 months ago. In fact, it's an old observation, and the paper only came back 3 months ago. It's not high resolution, but we're going to learn much more about it. So there's lots of interpretations of this, but I think the most reasonable one by far is when looking at the interaction of an outflow, and it's the boundary that we see. Okay. Okay, these are, talk a bit about, again, I'm just throwing scattershot, but relevant to our story, observations at you. This is what astronomers do, I'm afraid. They tend to throw you lots of strange jargon and words. But I did say there were 70 octaves of electromagnetic spectra around, and here's a good example. This is Carryin 421 again. And here we see from the lowest radio frequency, the highest energy gamma rays there. Okay? And what you commonly see in the sources like these with the jets, these are the ones with the jets, the blazers, the ones that are pointing towards you, is two humps in the spectrum, two features. A low hump here and a high hump here. And it's traditionally said that the low hump, it says this here. It's traditionally said that the low hump is synchrotron radiation, and the high hump is due to inverse Compton scattering. Inverse Compton scattering is basically where we have perhaps one of these photons here, perhaps something from an accretion disk, photon from an accretion disk, hit by a very fast-moving relativistic electron, and if it has that electron has a Lorentz factor gamma, or an energy gamma mc squared, if you like, then it will boost the frequency of that photon and the scattering, essentially Compton scattering in the red frame, by a factor gamma squared. So that boosted energy then gives you a gamma ray. That's called, sometimes called inverse Compton scattering. Not a very happy phrase, but it's the one that people use. So that's Compton radiation, that's synchrotron radiation. And there are these two humps here. I have a different name for them. There we go. So there we go. I call them Bactrian, and this is a very personal thing for me because I remember as a child, you have to learn names of things, and I was told in my elementary school there were two types of camel, and one was called Bactrian, and one was called dromedary, and like the AGN, some had two humps and some had one hump. And I could never for the life of me get it straight which one was the dromedary and which one was the Bactrian, but I knew that there was going to be some test, and I had to use it. I now know what the algorithm is. If you use the letter D, you put it on its side, it has two humps. And if you use the letter D and put it on its side, it has one. And so now you know the difference between them. You may know nothing about quasars, but you know something about camels. So that'll come in terribly useful. Okay, all right, there we go. Now I've emphasized that these are variable, particularly in the gamma rays. It's one of the discoveries of Fermi Gamma Ray Space Telescope, as well as the atmospheric Cherenkov telescope and the water Cherenkov telescope, which are ground-based rather than orbiting techniques. Basically, the orbiting technique, which is a satellite GeV energies, goes up to an orbiting satellite does GeV gamma rays, roughly, and the ground-based telescopes do TeV gamma rays, roughly. And that's a factor of 1,000, okay? 2 to the 10, as opposed to 2 to the 0. Sorry, 2 to the 1, excuse me, which is optical astronomy, okay? So gamma ray astronomy is a big deal. Thinking logarithmically, they should get all the resources. Okay, so gamma ray sources are highly variable. A good example is a famous supernova remnant, which I hope you've heard of, called M1, or the Crab Nebula. You've heard of that? That's the famous supernova remnant, probably one of those famous sources in the sky. And that varies on timescales of hours, which is kind of remarkable, but no more remarkable than what's going on in these active galactic nuclei. And what we think is going on there, and this is going to be important for my story down the road, this relatively low power source, the Crab Nebula, relatively low power, so 8 orders of magnitude less powerful than a quasar. This low power source accelerates energies to probably 5 peta-electron volts. Remember that, 5 peta-electron volts. You might say, what's peta? What's this peta stuff? Okay, SI, you know SI units. You know some of them. There's K, which is 1,000. There's M, which is 1,000,000. There's G, which is 1 billion. Billion is a bit ambiguous, but it's 10 to the 9th nowadays for almost everybody. And then there's T, which is 1 trillion, which is 10 to the 12th, also ambiguous historically, but now it's 10 to the 12th. And 10 to the 15 is P, a peta. And 10 to the 18, which I'll come to if I get time, is 10 to the 18 is exa. Okay, and 10 to the 21, which will also come to it this time, is zeta. And then there's iota, and then there's what I call Xena, but it isn't official, that's our unit, but you need 10 to the 27 if you want to go to the Planck scale. Okay. Okay, so the Crab Nebula varies in timescales of hours, 5 keV electrons emitting synchrotron radiation. There's the variation. Gamma ray bursts. Much of the gamma ray bursts, they produce jets as well. They're sort of supercharged jets. They can have Lorentz factors not of 30, but of 1,000. Okay, that's pretty remarkable. Okay, and they vary on timescales of milliseconds. Let's say Carryin 501, 2 to 10 minutes. Even more impressive, that's GeV variation. The GeV variation in another quasar this is the one that's most striking and the most constraining astronomically, it varies in 5 minutes. Which if you think about in the rest frame of the quasar, that's you taking out the cosmological redshift, that's 3 minutes. If you think about it in the rest frame of the moving material, remember this stuff is moving out at the speed of light, very close to the speed of light. That could well be 6 seconds. Okay. So, this is dramatic variation. These are great challenges to physics as we know it. These are all these variations here. Okay. Some other clues that we have, and I'm going to go very quickly through this. These are so-called quasi-periodic oscillations, a bit like in the 19th century where people found atomic spectra. You looked at various different atoms and you saw the spectral lines, and this was a great puzzle, and they had lots of empirical ways of describing it. We see similar sort of variations, characteristic of accretion disks around black holes in various sources, with characteristic periodicities associated with them. Lots of people have explanations for this, they're not the same, and we really don't know for sure what's going on. These are called quasi-periodic oscillations. Black holes, of course, have also been famous. As I said, there were 70 octaves of electromagnetic radiation, non-electromagnetic radiation out there, and black holes are also famous for opening up one and quite possibly two new windows on the universe, in the multi-mesher theme of the subtext of this meeting. First is gravitational radiation. This was the first one that was detected by LIGO Virgo. Well, LIGO then, now LIGO Virgo. 230 solar mass black holes coalescing. And now of course, we know six of those, and there'll be more coming very soon. And then one neutron star binary. Okay, there's a new window on the universe, and we hope to see the black holes and galactic nuclei doing similar things in a more leisurely way before too long. And then the other window that may have been opened up, as anybody who has not been comatose will have realized, is IceCube has claimed to associate neutrino, 200 TeV neutrino, with a particular type of blazar with this telephone number. And there's been one neutrino seen, and an awful lot has been hung on this neutrino. It's not, I'm actually on this paper, believe it or not, and I read it after it appeared, but because I'm on the Fermi team, and so and I thought the paper was actually pretty well, I didn't contribute not a word to it, but the paper was well written, and quite cautious about the identification. Some of the hoopla that came with it was a little more extravagant. But it is a possible identification with the blazar. It's credible, but not totally beyond criticism. But these are plausible sources, and there's a good chance that they are opening another window on astronomy. And by identifying, we know there's hundreds of these neutrinos around, we've seen those, there's a good chance that they're extragalactic, and this is probably the most plausible source. So we'll probably know within years whether or not neutrino astronomy of blazars is a real, you can write a PhD on that. Okay? So let's just summarize a little of what I've said here. Theoretically, everything depends on the Kerr metric, and we talked about those. There are observed black holes in X-ray binaries, in active galactic nuclei, and these new bands opening up. I'll say a little bit now. It's not terribly important for what's going to follow, but it's important. Is that when we talk about in the active galactic nuclei, and in fact in binary X-ray sources, we talk about the modes of accretion. we can distinguish, I think, 3 different ways in which gas can be transferred onto the black hole. The first is what I call the intermediate mode, and this is when the supply of gas is at an intermediate, a middling sort of rate. And what happens then is you make, we believe, a relatively thin accretion disk. It radiates, this disk radiates efficiently, so as gas falls inwards from one radius to the next, it liberates the gravitational binding energy of that fluid element. And so it radiates efficiently, so the overall efficiency per unit mass of energy released is about 10 or 20% of c squared. You know, which is about 10 billion times dynamite and about 100 times what you get from nuclear power. Okay, so put that into context. The low rate of supply, what happens there is it's very hard for the gas to cool on the timescale that it falls in. It has been generally supposed that what you make is a very thick accretion disk that is non-radiated, like in M87, where we just don't see these disks at all, we only see the jet. If there's time, I'll give a contrary view to this, but the conventional view is that you get a very thick accretion disk, and that accretion disk is supported by the pressure of hot ions. And close to the black hole, 100 MeV ions hold this thing up. Very high mass supply rates give you radiation-supported disks. So here you can make the radiation very fast. The trouble is you can't get rid of it. There's Thomson scattering there. And so the Thomson scattering traps all the photons and it gets carried into the black hole, perhaps. That's what some people think. It gets carried into the black hole with the gas. In practice, I think that most of it goes off, in these 2 cases, most of it goes off in winds and jets in this case. And this is all radiation-dominated gas dynamics here. So this is sort of plasma physics and that one's radiation-dominated gas dynamics. So there's 3 different modes of accretion. And then, and this is obviously implicit in the title of this talk, is this magnetic field. Magnetic field not only is something that we invoke as a last resort, is something that has to be there. There are instabilities associated with weakly magnetized accretion disks that essentially grow the field by dynamo processes on timescales comparable to a few orbital periods. In a few orbital periods, if you start with a tiny field, you'll end up with a very large one after a few orbital periods. This is called generically the magnetorotational instability. It's originally a linear instability, which is a sort of, it's just a message that you cannot ignore magnetic field in practice. It's a very strongly magnetized environment with highly nonlinear processes determining what's going on. And there's a lot of simulation of this. We don't have a complete description of it, but we certainly understand it a lot better thanks to numerical simulation. The bottom line is there has to be a lot of magnetic field in these environments. It's inescapable. And that magnetic field will exert stresses, which will give you power and torque. Let me just say a little bit generically about outflows, jets and winds, magnetized, from black holes and the accretion disks that attend them. Let me just say a little bit about that. That magnetic field can do 2 things to the gas that it encounters or gets attracted. First, it's going to be carried along by the gas. That's one of the precepts of MHD. It's going to be frozen into the gas, but it can do 2 things. It can lose its energy. The energy associated with the electromagnetic field can be lost either by pushing on the gas, which is a non-dissipative phenomenon. It just pushes on the gas, and so it just does work on it, but not in any dissipative way. And then the gas can then take the energy out of the magnetic field. The alternative is it can actually dissipate, which is like ohmic dissipation. There's essentially a current with a component along the electric field. There's an E minus E dot J. That's ohmic dissipation. That ohmic dissipation just gives local heating, and so that gas will then glow and may radiate. Both of those processes are important to understanding the astronomical manifestations of cosmic backgrounds. I like to use the word prodigal and industrious to describe these two phenomena, the prodigal being the anticipative and the industrious being the one that does work. But that's the sort of subtlety of the English language. It's not terribly relevant. The words aren't very popular either, but that's okay. So where am I now? Okay. Let me just say this slide, and then this is observing black holes. We observe them because there's luminosity associated with them. There's stellar activity. There's a disk photosphere. So this is the disk. We say that can radiate. That means it's like the sun. It's got a photosphere, it's got a surface from which photons escape. There's a wind. That also carries it, just like the solar wind, but on steroids. It's the solar wind, but it has a huge amount of power associated with it. We think a lot of what the power that's lost by these winds that can't radiate, either through trapping the radiation or not being able to radiate. In the first place, a lot of that is carried off in hydromagnetic winds, and so that's another way you can do this. And then there's the spinning black hole, and I haven't got to this point yet, but this black hole, as I said, the spin, rotational energy there for the taking in the electromagnetic field we extract it. So these different channels, and all of them are important in different types of galactic nucleus. At this point, I'm not sure where I am. As I say, I've got enough material here, arguably for 3 weeks, but certainly for 3 hours, and there are other speakers that are coming. How am I doing in terms of time? 15 minutes, okay. So to this point, as I say, I've got a lot more material, so we have a choice. I can talk about, so these are the things I advertised in the abstract. I can talk about, firstly, what is probably the main topic of this meeting, which is how to think about extracting energy from the spin of a black hole electromagnetically. So I can go through some of the physics of that. That'll be much more physics. The other topics that are sort of down the road, as it were, from this are ultra-high energy cosmic rays, talk about particle acceleration in jets, talk about the initial launching of jets, talk about what's going on in those sources that produce the broad ion lines, what's called the lampposts and so on. And all of those I've got, this is a sort of transition. Those are just, those are subjects in which my colleagues and I, that long list at the beginning, have been working lately. And I think we have new ideas, but they're not sort of accepted ideas, as it were. This is all very new. And so it's a different character from the rest of us. So what I'm going to propose to do is, of this 15 minutes, let's just do a bit faster, but not a lot, the physics of how to extract energy from black holes, spinning black holes, and then I'll go very, very rapidly. You'll be seeing the rest of the talk as from a passing railway carriage, as it were. You're going to see your slides go through at enormous speed, and I'll make a few words so you'll give some idea of what's going on. Okay? Will that do? And were you to hear the remainder of the talk, you'll be totally convinced by everything I said, and it will be all completely clear. But unfortunately, I haven't got time to tell you. Not true. Okay, all right. So let's talk about the accretion disks. The accreting gas has angular momentum, so therefore it makes a disk. And there are sort of this is a cartoon of what is probably a more realistic type of accretion disk than the ones that are in many sort of particularly analytical descriptions of them. So it's going to be messy, it's going to wobble around, it's going to have precession and so on. It's got a lot of magnetic field, it's created internally in the disk. It looks like the surface of the sun. You've got field lines, I would say flux tubes. Actually, there's a very nice picture which I was going to show you. Do Google Meerkat, a South African precursor to the square kilometre array. Do look at that, an image of the galactic centre from Meerkat. Just look at that and marvel at that. And this is highly relevant to what I'm saying, but on a much larger scale. So I meant to show it here, but I forgot. Okay. So basically what we've got is some sort of wind here, which is going to be a whole lot of gas that gets sort of globbed onto the open flux tubes, the ones that go out to infinity, rather than the closed flux tubes here, which are like coronal arches and so on in the sun. And so we get an active corona, we get a wind, we get a radius from the accretion disk, and so on. And then there's a tiny little black hole there in the middle, which is going to be also magnetized because currents around outside the black hole are going to trap magnetic field onto its surface. So this is much more a sort of mathematical idealization. This is one of these thick accretion disks supported by iron. I'm not sure that this is the case now. Not sure I ever was, but I'm better convinced it isn't what's true. But anyway, for this demonstration, you've got magnetic field lines that are trapped in this funnel here, made by this thick iron-supported torus here, and those electromagnetic field lines cross the surface of the black hole and extract that spin energy. That's the basic picture. How does it do it? Well, it does it essentially by unipolar induction. It's Michael Faraday who discovered it. There's his disk, you've probably heard of. Again, what you do is you take the equations of general relativity to get the Kerr metric, and then you take Maxwell's equations and you solve these in the Kerr metric. This is formally what you do. This is sort of a description of what goes on. Okay, thanks. Okay, so associated with this is a flux, which is the magnetic field times some sort of area of the black hole. Okay, this is actually done more formally. And then, according to Michael Faraday, if you change that flux, and that basically in this context means multiplying it by the rate of change of flux is just multiplying by the spin frequency. Omega here, at the spin frequency, that'll give you a voltage. So that's a characteristic voltage here. This is where the batteries come out. Okay, it's not 1.1 volts, this is more. Okay, and if we then say that makes a circuit here, so we've got magnetic field lines, fields are always green, so there we go. There's a mass, there's a spin, that's all you need, BMW if you like automobiles. And this black hole seems to have turned blue and become rather prolate, but never mind. I think that's PowerPoint that did that. So you've got this in here, magnetic field line, so you get a voltage across there. And you can think about this as a battery, just a little circuit like that. And say, well, what's the impedance in that circuit? It's just going to be the impedance of free space, which is formally 377 ohms, but if you do geometry a little bit, it's more like 100 ohms. So basically, the internal resistance of this battery is 100 ohms, and the load under these sort of conditions, where it's essentially a relativistic outflow, is 100 ohms too. E twiddles B in the outflow, is what it's saying. Okay? So it's just a little battery with a load and an internal resistance, you both have 100 ohms. So that tells you that the current flowing is going to satisfy this relation here, and that 100 there is just, this is just in SI units. The power that you get, some of it's going to go into internal resistance, it's going to be heat battery, which means it's inside the event horizon, it's just increasing the mass of the black hole. Some of it is extracted into the load, say if it's matched resistances, it'll be at 50-50, it's not far off. And it'll be twiddles VI or omega squared pi squared over Z naught. Okay? And that's what it is when you solve the Maxwell's equation. This is deconstructing it in the electrical language of the title of this conference. We do the exercise for the crab. Remember, the crab is a spinning object. This is non-controversial. The crab, it spins. It's a perfect conductor. There's no internal resistance. But you do extract the power into the load. The voltage works out to be about 50 petavolts. Remember, peta is 10 to the 15. And a key point here, and I'll keep harping on this, for all of these sources, the actual density of current carriers you need to carry the currents, remember this 50 petavolts now means 500 teramps. Teramps, 10 to the 12 amps. The LHC is 0.1 amp, for those who know particle physics, is 500 teramps. The actual charge density that you need to carry this is tiny compared with the amount of particles ultimately associated with this. Okay? That's the point to which I'll return many times. You take a quasar, you get 300 exavolts. The highest energy cosmic rays that are detected have energies of 100 or maybe 200 extra electron volts. So that makes this de facto a credible candidate for the acceleration of the highest energy, ultra-high energy cosmic rays. I actually don't believe that's where the highest energy ones come from. And I may have time just to allude to where I think they do. But it's certainly a good candidate, that's undeniable. An even stronger candidate on these grounds is the gamma ray burst, where you can get up to 10 to the 23 volts, 100 zettavolts. So that's easily ample for cosmic rays. The problem is, this is according to popular magazines, the brightest place in the universe, and it's kind of hard to escape from that environment intact as a cosmic ray. But there are people who believe that that happens. Okay. In trying to describe this a bit more formally, there are three approaches. One is to do fluid dynamics, treat the gas as a fluid, and then carry the field along with it just as a passive additive. That's what most people in practice do. It's not adequate for understanding the batteries. The second one is to use classical electromagnetism and just treat the Maxwell stress tensor, Poynting flux, and so on, and ignore the matter altogether. That's the force-free electromagnetic approach. I'll come to that. That's the one I'll talk most about. The third is what is important for the outer jets. We know has to be the case. It's an amalgam of these two, which is what we call relativistic MHD. It's where you've got gas in which current is flowing and it has inertia, and so that has to be part of the stress tensor. That gas here is not appearing here. It's the only purpose of the plasma is to supply charges for currents and space charge. It's not there for inertial purposes. In relativistic MHD, you need the inertia too. Okay, so here's the force-free electrodynamics in a curved space-time. Basically, I think you probably like a soccer ball there rather than a black hole. This is Brazil. And so you've got field lines supported by external currents. It's essentially force-free. And I'm just leaping straight into this. I'll talk about some more implications in a moment, but just leaping straight into it so you get the general picture. We're going to have this event horizon here. So there's an event horizon there, I should say. And material has got to flow inwards through the event horizon, and it's got to flow outwards along the jet. That means you've got to continuously make charges in some sort of magnetosphere outside the event horizon to keep the charges and currents going out in the jet and falling into the black hole. From the point of view of Maxwell's equation, Maxwell cares not what carrying the charge, as long as there's current there. Maxwell didn't know about electrons. Never mentions them in his book, actually, although he did know about kinetic theory, obviously. But it's just seen as a fluid, electrical current is just seen as a fluid, basically. For those of you who know a bit more mathematics, there's Hilling vectors there, and associated with these are just symmetries of the curve metric. Associated with the symmetries are conserved angular momentum and energy. And also, as a consequence of this, the current flowing between two of these are relativistically defined surfaces of magnetic flux. Think about these lines here as being surfaces of magnetic flux, with the field lines twisted around like that, like a barber's pole. You know what that is? Say a helix. Helix is probably a better word. Okay? So there's current going along here, it goes along the field. Doesn't go perpendicular to it, goes along the field because it's force-free. And there's electric potential you can define here. So these field lines are also equipotentials. And the rate at which they rotate in a stationary solution is fixed. It's a fixed angular velocity. It's roughly about half the angular velocity that I originally introduced to talk about the black hole. The black hole has a defined angular velocity. The angular velocity of the field lines here is roughly about half the angular velocity of the black hole. There are boundary conditions, which are essentially the electromagnetic field is well behaved for an informal observer. And the key thing here that confuses many people is that you say, well, energy can only flow into a classical black hole. True. If you look in a non-rotating frame with respect to the distant stars, you see energy moving out of the horizon. That's what you measure, that's what you calculate. However, if you're a physical observer hovering just above the event horizon, rotating the angular velocity, you've got a Lorentz transform. So it's not just, it's like velocity, it's just like, momentum and energy, you've got to mix the two. In this case, it's angular momentum and energy you have to mix. And in that case, if you're spinning with the black hole, you'll get energy flowing into the black hole. So the flux of energy is into the black hole. So your preconception about what black holes do is correct for a physical observer. For a non-physical observer, in the frame in which the energy flux is conserved, is energy coming out of the black hole. That's the mechanism. If we do a circuit analysis between two of these flux tubes, what I said schematically, you can define the resistance of the black hole, you define the resistance of the load, and this is the compromised angular velocity that you get. It's just simple circuit analysis, the most elementary type of circuit analysis, that's all it is. Okay, to think about it in a bit more detail, to write down Maxwell's equations, but write them in an unfamiliar way by putting on the left-hand side the time-dependent part, then put in the fact that if there's no inertia there, the electromagnetic stress must vanish, divergence of the electromagnetic stress must vanish. Another way of saying that is rho E equals J cross B vanishes. That says there's no electric field along the magnetic field, no work done on the matter, E dot G must vanish. And then you use that to solve for a constitutive relation for the current density, which is given by this expression here. That's just exercise for the students. It's just manipulating Maxwell's equations. Okay? It's an evolutionary system when it's treated relativistically. Electromagnetic stress is pushing electromagnetic energy around. There's no inertia. Keep saying that. Okay? It emits, as it's a sort of mathematical problem, it emits characteristics in these, in the hyperpositive differential equations, and these correspond to fast waves, which are basically just electromagnetic waves, and then the other polarization, which is an alpha wave, which carries energy along the magnetic field lines and has current associated with it. These waves may steepen, that's relevant to particle acceleration, and I actually believe in a quite different talk is what's going on in the so-called fast radio bursts, for those who know what that is, for these waves. Okay, this of course has been simulated now. There are impressive simulations. These are not the most impressive because these are older ones, but they're good enough. They show this mechanism working, solving the Einstein-Maxwell equations in a curve space-time. They make ad hoc assumptions essentially about the gas that's orbiting this. In this case, it's making fun. If you put in the funnels by hand, you have magnetic field lines, and you find out some things about the behavior of the jet. So here's a simulation. This is a simulation I can show you later. I'm not going to show it now. I probably haven't got time to do that. But this is a long simulation that shows how these bets behave. It actually, the simulation pointed to physical behavior that we hadn't guessed beforehand, and it turns out it's right. So the simulations can be used as discovery tools, not just giving you the cold truth. Okay, you can observe these simulations by making ad hoc assumptions about what the emissivity is associated with the outflowing material in the inner jets. And you put in some well-described prescription for saying how particles are accelerated. We know how they radiate, but how they're accelerated. And you can say, well, then what would a radio telescope see? And already this is making predictions. Here's one. If the field is helical like that, and synchrotron radiation you're looking at, then you should see one side brighter than the other because the pitch angle is different for the electrons you're looking at. So this is just one out of many examples of what can come out of this, about it. So this is onto the sort of material that is going to be viewed, as I said, from a passing railway carriage. So this is very much a work in progress, but I think the evidence now is very much against these so-called thick iron-supported tori in the low power accretion disk like NM87. Instead, the accretion disks are thin all along, but they are very highly magnetized. And new processes are going on in these sources. And I think, we've thought some about this as have other people. I'm not sure this is the right answer, but it's looking, to me at any rate, a lot more promising than it did 10 years ago. And we're driven here by observations. I said something about the lampposts. These are the sources that produce these broad iron lines that are the primary evidence for rapidly spinning black holes. What the observers say is that the source of the X-rays that illuminate the surface of the accretion disk and cause it to fluoresce, so you get off the iron lines in this way, with the velocity and gravitational redshift of the disk, that source is typically located above the black hole. That's not a good place to do engineering. It's supported there by pure thought originally. So the question was, what's going on physically? And they call this the lamppost. It's their expression for this. And so they call this the lamppost. And the idea that as Jürgen and Wilkins and I have been pushing is that as well as these field lines that come out of the disk that drive the wind, ones that are directed inwards. So if you imagine this is the accretion disk, that's the black hole. Instead of the field lines like that, field lines that look like this, those field lines will have matter dragging the field lines inwards because it's unstable for the matter to go inwards on those field lines. And then those field lines will meet around the axis of this black hole, the spin axis of this black hole, and they'll get, this is an American expression, it's wrapped around the axle, they say. It basically means you don't know what you're talking about in American jargon. So this is the wrapped around the axle model, and so you get these field lines wrapped around like this, they'll be reconnecting like crazy, they'll make, at this sort of region, they'll make a lot of dissipation, probably a lot of hot plasma making X-rays that can radiate the disk. That's the story. Okay. Okay, here, gamma rays and pair production. This is a really big problem and puzzle in these disks. I said we've got these rapidly variable gamma rays, so let's make them close to the black hole. The problem is we believe in quantum electrodynamics. A TeV gamma ray will pair produce on a 1 eV photon. And we know what that cross-section is. In the case of the quasars, we know how many photons are there too, because we see them, we measure them. And they can only come from outside some region where they can escape, those gamma rays. This is a really big puzzle. It's much farther away and can vary on timescale of minutes. It's a really big puzzle, and I'll say a little bit more about this. So, for what isn't a big puzzle, I think, is how to make these pairs inside the magnetosphere. There has been a lot of work done lately. Somebody may talk about this here. I'll just sort of summarize it briefly. You don't have to expend much of the power doing this. As I said, it's a trivial amount of plasma. You need to carry the currents. But just say that there's been a lot of work recently, some of which may be discussed here, on what's going on in terms of relativistic plasma physics in those magnetospheres. What I would have liked to say more about, because I think this is probably the most revolutionary of these ideas in some sense, is that remember I talked about the camel and the two humps, and the second hump, and I said, well, everybody assumes that's Compton scattering. And that's still the case, but I'm actually proposing that it's synchrotron radiation. The second hump is mostly synchrotron radiation, not Compton scattering. So how do I do that? The reason for doing this is because if you believe these jets, the inner parts of these jets are highly magnetized, it makes no sense to make that second hump be Compton scattering. It should be, it's too much magnetic field for it to be, it should be, you know, in the way over the ceiling. So, essentially, here's the schema here, is that you accelerate a proton to 100 peta-electron volts. Remember, you've got up to a zettavolt available in these environments, so it's not a lot, but you accelerate protons to those high energies. Then the dominant process that I believe is that, my colleague was thinking about it as well, is that in the Coulomb field of that proton, its rest frame, 100 milli-electron volt means 100 microns. It means a far infrared photon, which we see. This is the peak of the so-called synchrotron hump. Those photons produce pairs. It's not pions, they make pairs. And those pairs, you'll make 1,000 of them, call one of these particles, the 1% of the Thomson cross-section. And when you've made these enormously energetic electrons, they then cool by synchrotron radiation, and that makes the gamma rays that you see. Initially, those gamma rays can't escape, so you make a shower. You make a shower. The gamma rays make pairs, which make gamma rays, which make pairs, until they can escape, so they escape where they can. And it makes the 3D photons. So the cosmic rays, here's the cosmic ray spectrum. There's your zeta electron volts. There's the energy of the highest energy cosmic ray. That's from last night's football game against El Salvador. Hope there's nobody here from El Salvador. And it has the energy of one of those goals, but the momentum of a snail, these highest energy cosmic rays right up here. And those are the ones that are in the title. Okay? So these are the potential sources that, well, people normally say, actually, I don't believe in that anymore, and I don't believe in that. But that's what they say. That's what I believe in the process. Okay, so where we got? Oh, that's shock acceleration, shock acceleration. This is the Perseus cluster. That's what it looks like on the night of Halloween and actually afterwards. And these are the X-rays, and basically it's an accretion shock around that cluster of galaxies. I would argue the site of the very highest energy cosmic rays. How do you do the particle acceleration under these environments? This is a phenomenon. I would use the phrase, it's only a slogan, it's not a mechanism, called magnetoluminescence. You essentially got this electromagnetic field, we want to convert that into high energy particles. What I think, there's been a lot of work done on relativistic reconnection, just shown schematically here. This is field lines and they exchange partners very often. I believe this is a very efficient, steady process, relativistic reconnection, but it is rather slow. You have to wait to get all those field lines processed through a very small region. So it doesn't happen very fast. But those field lines can recreate and make high energy particles. What I think is probably more important, whoops, where did they go back there? I think it's probably more important is to, instead of making something like this, make flux tubes like this, instead of making a flux tube like that, which has to resolve itself by reconnection, by having field lines cross one another, they've got to reconnect, got surgery, in a topological sense. You can instead have a slip knot, you can have these things. That's actually a good analogy, a rope, a sort of hairy rope is a good analogy. And you can resolve that slip knot. That releases a lot of magnetic energy at the speed of light without any topological constraints. That volumetrically accelerates particles to enormous energies. That's what I would call magnetoluminescence. We've done some simulations of that before. The future is bright. I think we talk about the Event Horizon Telescope, now anchored by ALMA, the millimeter telescope. It's doing millimeter, and we'll shortly do sub-millimeter observations with telescopes, essentially in a global array. Greenland is there. It's missing from this diagram, but Greenland is there. It'll produce, depending on how you measure it, few m, that's the radius of the orbit resolution for M87 and Sagittarius A star, our galactic center. That's, I think I've lost something. Okay, I've lost an image there, never mind. That's the a numerical simulation of what they'll see. But no, they won't see anything like this, but in principle, that's what they could see. And so we're actually going to learn a lot. Those data, this isn't something in the distant future, those data were taken last April. They already exist. It'll take a year to analyze them, probably another year to get everyone to agree about what's in the paper. But it's, before long, you'll see images all over the newspapers of M87 and Sagittarius. The summary, this electromagnetic effect should be there, and they seem to be very efficient for making the jets and much of the power that one gets from these quasars. There are major challenges, I've just listed them here, and IceCube is obviously coming of age. We'll see what comes of that. Cherenkov telescope array is under construction. Some part of it isn't yet under construction, will be in Chile. There's a lot, and Water Cherenkov telescope is a new facility called HAWK, which is under construction in Brazil. I think is involved in a plan to build a southern hemisphere version of HAWK, which would be great. Simulation is great. So all of these things, we're going to learn a lot from direct observations of black holes, I think, over the next few years. So it's a good subject to work in. One isn't waiting 20 years for some dream. It's happening as we speak. These things are happening. Okay, thank you very much indeed. Sorry for going on slightly long.